Hi, everybody. Welcome. My name is David Watson. I'm a postdoc at the UCL Department of Statistical Science. And today I'm going to talk a bit about interpretable machine learning for genomics, focusing on applications in molecular biology in particular. But I think actually a lot of what I'm going to say is quite general with applicability to other instances of interpretable machine learning, specifically kind of opportunities, challenges, and future directions for this area. So start just by giving a bit of an overview of sort of topics I'm going to discuss here today. First, just a few words on background and motivations. I'm going to say a bit about what machine learning in healthcare looks like today and how interpretability is already being brought into the genomics research workflow. But I also want to talk a bit about the motivations behind this. What really are the reasons that we do this, and why does that matter for how we design these tools moving forward? I want to highlight three key challenges that I think are currently not sufficiently addressed in this literature, and that I think are going to be important as we continue to refine these tools, especially in medicine and genomics. And I'll just conclude with a few thoughts on future directions for this area of research. So I'll start by kind of diving right in with interpretable machine learning. This is probably going to come as no surprise to people in the audience today, but medical AI is already here. This is not about the future of medicine. This is very much about the present of medicine. There's a ton of examples we could point to. Perhaps the most obvious and striking are these sort of visual examples. So anything based on visual scans in radiology, good examples in retinal scans like diabetic retinopathy. This is an example from a Nature paper a few years back, obviously looking at mammograms and tumor detection. These are the sorts of tasks that deep learning models, in particular convolutional neural networks, are very good at, as good if not better than human experts in detecting, for instance, tumors. So this is stuff that's already being used in clinical applications, and I think we'll only see more of that moving forward. But it's not just these sort of visual examples. There's also lots of really interesting use cases in genomics in general, molecular biology in particular. So there's an example from an influential paper appeared in Nature a few years back by a group at University of Toronto trying to predict sequence binding events. We see lots of this work using, again, convolutional neural networks, also recurrent neural networks, to predict these sort of complex patterns at a really fine-grained molecular level, giving us some intuition for things that would otherwise be quite difficult, I think, to parse. Most recently, there's been some really exciting work in antimicrobial resistance prediction and antibiotic discovery. This is also built, in this case, on deep learning. I'm not going to say too much about the machine learning tools themselves, like the architecture of deep learning or other popular methods like random forest gradient boosting. I'm happy to talk about that a bit in the Q&A, but I'm imagining that most people are broadly familiar with these tools. A wide variety of them are used. I think all these examples I just used were from deep learning, but there are a lot of different tools out there. And they're doing very interesting work, very different sorts of work. That's the other point I really want to drive home, is the heterogeneity of methods and of results. But also just to highlight that this is already getting used not just in a sort of research setting, but in a clinical setting as well. So it's not just the machine learning tools that are already here. Kind of hot on the heels of that, there's this interpretable machine learning sub-discipline that's kind of emerging as well, and also being applied in medical settings. I'm going to say IML, interpretable machine learning. Some people say XAI for explainable AI. I consider those interchangeable. Maybe someone else has a more fine-grained parsing here. But these are broadly just tools that are going to make the predictions of these complex statistical models, like those I just showed some examples from, perhaps a little bit more intuitive and useful for end users. When the data and model are very visual, as in the sort of early examples, the obvious direction to go would be with these sort of saliency maps. So a saliency map like this one is just going to highlight what regions of an image led to a particular prediction. So these are the sort of reddish parts on the right here are going to be the more tumor tending, tumor inclining regions of this pathology scan on the left. This is based on a whole suite of technologies, a lot of sort of layer-wise relevance propagation, propagating gradients. This is very much tailored specifically to convolutional neural nets because they are the most popular function class for these kind of imaging tasks. But there are more generic alternatives. For instance, Shapley values have become kind of the de facto standard in interpretability. And I'll say a little bit more about Shapley values a little bit later in this talk. But basically, these are a kind of local linear approximator. LIME, which is kind of the first big paper in this area, is another popular local linear approximator. The way these methods work is that they're going to find, for a given input point, the best linear approximation of the regression surface or decision boundary near that point. So even for a very complex kind of wiggly function, we can find a linear tangent at any given point, and then we can sort of interpret the coefficients of the input features describing that model, that linear model, as importance measures. And this is actually proven quite useful in lots of settings. This is an example from a clinical paper. We can see a nice sort of interaction effect here between white blood cells and blood urea nitrogen that comes out quite visually. But this is also widely used in more molecular settings where the data is much more high dimensional to sort of screen important variables, maybe transcripts or something, and zero out less important ones to give some intuition for what is happening to predict these diagnoses. A final example I'll just sort of point to is actually probably one of the oldest and more familiar examples. These are rule lists. So this is from a paper in 2015, which is basically the dark ages as far as this field of literature goes. But it was a group that put together this idea of falling rule lists. So it's falling in the sense that stroke risk, which is the target variable, is monotonically decreasing in probability as we move down the list. And the motivation here was to get a rule list that could fit on an index card, so could have some kind of clinical viability. And this model actually outperformed the state of the art at the time in predicting stroke risk based on just a few conditions that were all sort of interpretable as if-then statements. So these sorts of things, these sort of visual outputs, linear models and rule lists are seen as kind of canonical examples of things that people are fairly good at interpreting in general. So when we try and interpret these complex either deep learning models or maybe forest ensemble models, it is these sorts of reduced models that we tend to favor in the explainability literature, for better or worse. Perhaps those last few slides suggested a few ideas on what people are getting out of this, why we like to explain in the first place, but I want to be really clear and specific about our motivations here, because I think once we start thinking critically about why we're explaining, we can resolve some potential issues that come up later. So the first one I want to point to, which didn't come up so much in these previous examples, but is quite commonly cited in the sort of computer science literature, especially around fairness, accountability, transparency. There's been a lot of conferences in that area. And this is about auditing algorithms. So it's known that health outcomes are unequally distributed. This image on the right here is from a big influential paper in Science that appeared a few years back, where a team showed that a very widely used healthcare screening algorithm was sending white patients to the doctor at much higher rates for a fixed number of active chronic conditions than black patients. And this is resulting in very unequal health outcomes for these two subgroups. And I think you would find broadly similar things if you were to look at socioeconomic status or other sort of breakdowns in different countries. We know that health outcomes are unequally distributed, and there's lots of complex reasons for that. But the concern is that bringing in algorithmic tools might automate those inequalities. And to bring this kind of to a molecular level, we know, for instance, that white Europeans make up some 15-16% of the global population, but approximately 80% of all GWAS subjects. So as we move into an era of precision medicine and using sort of polygenic risk scores, for instance, the very legitimate fear is that this could augment existing inequalities in healthcare. So IML tools can potentially protect against this algorithmic bias by identifying it, finding out if these sensitive attributes are what are driving predictions in a lot of cases, and even mitigating against it. And this may have legal force, by the way. At least in Europe, the 2018 GDPR, this is a subject of some debate among legal scholars, but it may include language giving a right to explanation, a legal right for all data subjects. And I think we're seeing similar regulatory frameworks gaining popularity in other jurisdictions as well. Another motivation, kind of pivoting toward the more epistemological now, concerns validation. And the concern here is that supervised learning algorithms, sort of the off-the-shelf tools that are just empirical risk minimizers, like a neural network or even linear model, random forest, whatever it may be, are bad at handling confounding. So to take a sort of famous example, there's a paper by Caruana and colleagues at Microsoft Research a few years back now, where they teamed up with some doctors at Mount Sinai Hospital in New York to try and predict health outcomes for emergency room patients. And they were surprised to see that their model, which performed very well in all their tests, was predicting better than average health outcomes for asthmatic patients who came in with pneumonia. Now, this was a big surprise because that's actually a very risky condition for that subpopulation to have. But it wasn't an error so much as a result of confounding. It is so risky and so known to be risky for asthmatics to have pneumonia that the doctors were routinely sending those patients to the ICU immediately, where they were receiving extra attention, extra care that tended to improve their health outcomes on average. Now, that's an interesting sort of quirk in that study, but it's a potentially dangerous idea if you were to extrapolate that out. So say you use that algorithm in a new environment where it is just sort of automating decisions and we don't have this extra oversight from experienced doctors. Well, that algorithm may recommend treating these patients as low priority because they have good health outcomes on average. Now, it's not explicitly modeling why, and the reason why is this confounding. There's a common cause, and that's what this sort of DAG image here is suggesting. When you have a common cause, it can make it very difficult for a supervised learning model to identify what is driving that outcome. Some models, I should note, do try and ameliorate this, so as a sort of Ivy model or any kind of structural equation model, this is exactly the issue that those are getting at. But those are not the most commonly used algorithms we see in supervised learning today. We see more sort of off-the-shelf methods. IML tools can help protect against this kind of overfitting and spurious signals. And it's actually, this is probably the most popular use of these tools among computer scientists, is just to sort of troubleshoot and see what is driving potentially erroneous predictions. That's another key use case for these tools. A third and final motivation that I just want to name, I think this is actually probably the most popular choice in molecular biology, how these tools tend to be used, is for discovery. So in the first two cases, we were sort of assuming that there was something wrong with the model, or at least we were wanting to investigate a bit further to see if there was something driving erroneous predictions. In this case, we actually assume that the model is more or less right, or at least it's outperforming human experts. And we want to learn why. What exactly has the model picked up that we don't know about? So this image is from a recent paper appeared in Nature Scientific Reports where the task was AMR prediction, so antimicrobial resistance, and they were using some sort of sophisticated ensemble models, but then they wanted to use an extra sort of interpretability tool to extract a rule list, this time depicted as a sort of decision tree for particular predictions. And the idea here was that even though the model was quite complex, you could, in particular cases, derive these fairly short rule lists that could help reveal mechanism a little bit and tell you what particular, for instance, RNAs were driving these individual outcomes. So this, I think, is where we're going to see a lot of focus and attention in genomics for years to come, is on bringing IML tools into the toolkit for revealing mechanisms and suggesting hypotheses. I don't think it's an answer unto itself, but it's something that can be used as part of the workflow to suggest new experiments potentially. So that's maybe said a few words about opportunities and how these sorts of technologies are being used today. I want to focus now a bit on the challenges associated with this, because I don't think everything is roses up here with interpretable machine learning. I think there's some serious problems that need further consideration. And the first I'm going to discuss is this issue of ambiguous targets. So what I mean with an ambiguous target is that it's not always obvious when we use one of these IML tools whether our goal is to say something about a system or a model. And when I'm contrasting systems and models, what I have in mind is something like this. Say you've got 4 predictor variables and an outcome variable y. It may be that your underlying structure, your true data generating process, looks something like this. This is just a DAG, a directed acyclic graph, where you've got a bit of complexity. You've got a collider, you've got a mediator, you've got some variables with multiple edges coming out, some with just one, and only 2 of our predictors have direct edges into y. And this sort of thing happens all the time. And in fact, in a higher dimensional system, you could have a much more complex set of incoming and outgoing edges depicting causal relationships between variables. But a supervised learning model, an empirical risk minimizer, like I was saying earlier, always implicitly assumes this data generating process where all of your predictors have arrows into y, and there's no explicit modeling of the interrelationships between those predictors. Now, these edges can be more or less strong. For instance, a lot of these sparse models, like a lasso or something, are going to zero out some of these edges. But the important point is that it's not paying attention to how the variables relate to one another, the input features. So in an explainability setting, to take a very concrete example, look at something like SHAP. The default setting for SHAP, which is a very popular implementation of the Shapley value algorithm for feature attributions, assumes this independence between predictors. That means that we sort of marginalize over the empirical distribution for a given predictor when calculating these Shapley values. That assigns equal weight to impossible data points as it does to highly probable ones. So we might be looking at, pregnant men or teenage grandmas. Those are all plausible data points as far as SHAP is concerned, in so much as it treats age, pregnancy, gender, and status as a grandparent as independent variables. Well, in fact, they're not independent variables. And so if you want to model the system rather than the model, you need to take those dependencies into account. Now, there's been a lot of literature in the last few years on which view is right, quote unquote, the sort of system view or the model view. And I want to posit that that's really a false dilemma. And that's what the horns of Bessie here are trying to suggest to us. So the false dilemma is that one approach is going to be superior to the other. We're always more interested in the system, or we're always more interested in the model. And this is just a random sampling of some of the literature in the last few years that have tried to take a strong position one way or the other. The reason I think this is a false dilemma is that each offers the right answer to a different question. So the methods are really complementary. And this is where we kind of got to go back to the motivation. If you're interested in just performing an algorithmic audit, well, then you're probably more interested in what the model knows than in what the system is actually behaving like. So it may be that there is no relationship with race, let's say, and some health outcome, but you're just trying to find out if the model thinks there is. Well, then treating the variables as independent, if that is in fact how the underlying target function behaves, is the right quote-unquote choice for that problem. If you're interested in using these methods for discovery, which again is the kind of more popular use case in genomics, well, then you're actually going to have to care quite a great deal about the natural constraints placed on a data generating process by, for instance, biology. So it's really about paying attention to what brought you to this inquiry in the first place and using the appropriate tool. And I think that's really the solution here, is making sure that you're using the tool that best matches the goals. So all of these different methods can sort of live together and be complementary. We just need to pay close attention to which one we're using at any given time. A second issue that we're going to need to address is this issue of severe testing. So that's a terminology that is highlighted by Deborah Mayo, who's a philosopher, has written a lot about this in the last few years. I think it's a very intuitive idea. It's one that'll be very familiar to anyone who works in the applied sciences. We just say that a hypothesis is severely tested with some given data set if and only if the outcome of the test accords with the hypothesis. And with high probability, that test would have produced a result that accords less well with the hypothesis were it to be false. So this is just another way of saying we want tests that are sensitive and specific, right? We want low false negative rates, low false positive rates. It's impossible to get both at zero simultaneously for the most part. So there's some sort of trade-off involved. We tend to fix one and minimize the other, or try to perhaps minimize both jointly. This is how statistical inference works, right? This is very familiar territory if you've ever worked in this area. Frequentism, which Deborah Mayo is a very proud frequentist, so she's going to frame this primarily in the sort of a Neiman-Pearson framework, does this quite explicitly. We fix a false positive rate alpha, we minimize a false negative rate beta. But I want to stress that this is not unique to frequentism. Bayesians perform something very similar with a different toolkit. We're going to talk more about Bayes factors, credible intervals, predictive distribution checks. There's a really nice paper by Gelman and Shalizi where they sort of cash out Mayo's severe testing regime in a purely Bayesian framework. Now, like I said, if you're familiar with working in genomics or really any science, natural or social, you'll be very comfortable with the idea that you're going to need to report maybe a p-value, maybe an effect size, Bayes factor, the power of the test. These are how we sort of evaluate the reliability of given results. There is no semblance of this basically in interpretable machine learning right now. There's a few exceptions which we can talk about in the Q&A, but they are notable for their scarcity. This is really not how Shapley values tend to be reported. For instance, we just give a number. We don't give a p-value, we don't give a confidence interval or a credible interval. The solution, it seems to me, is that really we should have no explanation without inference. These tools, be they rule lists, be they saliency maps, we need to know how reliable they are in given use cases because not all explanations are going to be of equal value. So we need to assess that and really evaluate the uncertainty of a given explanation on a case-by-case basis. A final point that I want to make, a final challenge to raise, is this issue of product versus process. So a lot of current methods are really interested in treating explanations as some sort of static deliverable. I want to posit that maybe it's more useful to think of explanation as a dynamic process. So it's a bit more about the journey than the destination. In analytic philosophy, it's very common to think of an explanation as a kind of argument or a kind of model, and then to think about what structural properties those arguments and models have. In statistics, we tend to focus more on parameters, maybe plots. There's a lot of like visual explanations that are used in statistics, but you might call a prediction explained once you spit out a bunch of numbers. There's a more ancient tradition, though, where explanations are a certain kind of interaction between agents. We see this going back to Socratic dialogues and things of that nature. But you don't need to just look at the literature. You can think about interactions with a child, if you've ever had to explain to them how a certain word is used or how a certain natural phenomenon occurs. There's a lot of back and forth. There's lots of follow-up questions. It's not just children, by the way. This is how a lot of science unfolds, right? We need to be engaged in a ongoing dialogue to make sure we elevate an agent to understanding with respect to a particular, in this case, model prediction. So the solution here, it seems to me, is to replace explanations with explanation games. And I've written a bit about what that might look like in practice. There are a few methods already that implement some sort of more flexible, customizable option. And I think that's an important direction moving forward. So I'll just conclude with a few sort of summary points and ideas about what the next steps in interpretable machine learning for genomics might look like. First, I think we can all agree, that medical machine learning is here to stay. It's really about making the most of these tools in the future. Misleading explanations can be avoided with tools that are clear, rigorous, and flexible. So clarity is really a point about making sure we're not ambiguous with respect to our target. Rigor is a point about those statistical methods, making sure that our explanations are reliable. and flexible in the sense that they are tailored to the needs of an agent and the result of an iterative process rather than just a static deliverable. The other point that I want to make is that, these IML tools are often motivated by concerns about trust. Why should we trust this given model? Why should I believe this diagnosis? I want to say that it's not obvious that tools like Lime and Shap solve that on their own so much as move the problem one rung up the ladder. Why should we trust the outputs of these algorithms themselves? At least a target function has the advantage of having some known error rate. With Lime and Shap, if we don't quantify that uncertainty, if we don't subject that to some rigorous testing, it's not clear why I should believe those explanations any more than the original prediction in the first place. Finally, I just want to note that feasibility is a legitimate concern. In genomics, we're often looking at dimensions on the order of thousands, maybe millions. Sample sizes can be very large, especially in like GWAS studies. But when the stakes are high, we really need to get the explanation right. And I think that's the most important thing to remember. It's valuing efficiency over accuracy really does us no favors, especially in medical settings. So I'll conclude there. Thank you very much for listening to my talk today, and I'm happy to take any questions or comments at this time.